Hello, this is part 2 of a two-part series, and we're in the multiple linear regression setting and we're looking at influential measures. Now in part 1, I showed you the 7 built-in functions of R that examine outliers and influential values in multiple linear regression. And so we have 3 of those 7 left, and that's what we're going to cover in this video. And the first one is dfbetas, stands for the difference in the betas. And so you have a model and you fit a regression line to it and you come up with a model. And you'd think that if you just delete one observation and recalculate the model, that it wouldn't change much. But if it does, then something maybe is wrong with that value. And we call that value an influential value. And so one way to see if the model changes is to look at the difference in the betas. And so df beta calculates the number of standard errors that the least squares estimate for beta j, which is a component of that least squares vector for the beta parameters, changes if the ith kth is removed. You'd hope it doesn't change much, but if that value changes a lot, then something is weird. So from previous video 36, now this video is in a playlist called General Linear Models Regression, and in the 32nd video of this playlist, we calculated the variance of one of those beta, the least squares estimate of one of those betas, so beta j, and it was this, where cjj was the jth diagonal element of this. So then the difference of the beta j's, and we have subscript j and I, because so each observation, there's k plus, or k regressor variables, and so when we keep and remove that ith observation, we have to look at k different beta parameters. And so that's just a reminder. That's why the subscript j I is there. But it's the difference in the beta values, the least squares estimate of the beta values. So with I in the model, with I not in the model, and of course divided by the standard error. But since that's an unknown parameter, we have to estimate it with the data. And we estimate the standard deviation without the ith observation in there. Because if the ith case is a weird case, it may artificially inflate this standard deviation, which then kind of artificially shrinks this number. So this is it. Now the rule of thumb for df beta is this: if the absolute value is greater than or equal to 2 divided by the square root of n, we classify that observation as having high influence. And that's it. But to me, one of the interesting aspects is it looks like we have to fit different models for each observation. So, we keep and remove the first observation, keep and remove the second observation. But this theorem says that we only need to fit one regression, and then there's ways to go in and back calculate these df betas from just one regression. So it really makes it fast to calculate all these things. So here's the little proof. So let X be the design matrix, and these script X's are the rows of the design matrix. And so the transpose is this, and we're going to let R be this value, X transpose X inverse X transpose. And we're going to let Rj be the jth row of this matrix. We're going to let gamma j be a vector of zeros with a 1 in the jth component, otherwise all zeros. Now let's look at R in a little more detail. So this X transpose, we're going to put in this for it and see what we get. So now this X transpose X inverse can actually be multiplied into each column. So this has in columns, and you can think of it like this. Now let's pre-multiply R by gamma j. And what that does is it picks off, remember it's all zeros except for a 1 in the jth component. So it picks off the jth row of R. But you can also think about it is then this gamma gets multiplied into each column like this, right? So if we just isolate on this one, remember this is the ith column, and then multiplying by gamma j, it picks off that jth component of this ith column. Okay, and that's going to come in a second. Well, so what I just said is RJI. Remember, this is the ith column, and we're picking off the jth component. Now, if we look at R transpose, it's this, but since this is the identity matrix, it kind of goes away, and we're left with this. So that means if we look at the jth row and the jth column, then it isolates that jth diagonal. And that's what we were calling CJJ earlier. It's the jth diagonal element of this matrix. So from previous video 65 in this list, we derived this condition here. Now EI, and that's my dishwasher in the background if you can hear that. This EI is the ith residual. So now what we do is we pre-multiply by gamma j, gamma j, gamma j. So what this does is it picks off the jth component of that least squares vector, and it picks off the jth component of the least squares vector when we fit it without the ith observation, and then we stick it right here. Well, right, this is part of dfbetas, but what does this represent? Well, this piece here we were calling RJI, of course the residual, and that stays the same. So the dfbetas can be thought of as, it is this, but now we substitute this in for the dfbetas, and we get this. Now everything in here is, we only need one regression to fit, right? This is from the full model, full model, full model, full model, full model. And we showed in previous video 65 that this can be fit with the full model. So for each observation, we only need one fit to go back and calculate these dfbetas. And that's kind of intriguing. So now, one downside about this. So for each observation, we have to look at k or k+1 betas and see how they changed, right? And that's a lot of looking. So what Cook's distance tries to do is to summarize for each observation. It gives us one number to say, hey, something went awry when we removed the ith observation with all these betas. So now go back and look at the individual ones. But if it's not flagged in Cook's distance, then we don't need to go back and look at the betas for that ith observation. And so it's a quick way to summarize these dfbetas. So note that for each observation, dfbeta creates k+1 statistics. Cook's distance is a single measure of influence of the ith case on all the betas simultaneously. Now a little background. This is based upon a derivation we did in previous video 36, where we derived a simultaneous inference on this vector of unknown beta parameters. We created a confidence region for beta with this statistic. So now this is the least squares estimate, and then what we did is we found all the betas that satisfied this, and then that creates what's called a confidence region for that vector of unknown beta parameters. And Cook's distance is sort of based upon this. Cook's distance is this. So instead of the unknown beta parameter, they put in the df beta right here, that value that we obtained. Or not df beta, but it's the least squares estimate without I and with I. And it creates this. So we get a number. So now, what number do we have to notice before it's flagged as influential? But before I state that, I want to note that DI does not follow an F distribution, but you can maybe think of it as F-like. So sometimes we say, hey, this distribution is T-like, And so we can use a t-distribution to come up with, a criteria. And it's a rule of thumb as opposed to an exact calculation. And that's what this is. So if the Cook's distance is greater than this value, so normally we would put alpha there, it's like 0.05, but here we put 0.5, and then numerator, denominator, degrees of freedom. If Cook's distance is bigger than this, then we classify that case I as influential. Then we have to repeat this for each observation. Well, it turns out that all n Cook's distances can be calculated from one regression, and it's actually straightforward to see. So from previous video 65, we derived this formula, and then we put this in for Cook's distance. So this goes, it's right here. Now that's a number, it's a residual, so we take it and it ends up being squared, and then this ends up going right here. That is this part. It comes in squared because we add it in the beginning and the back, and then that is just part of Cook's distance. Well, this can be simplified to, now notice that this and this is the identity matrix, and then what's left over is the hat value. We have the residual squared, and then in the denominator we have k plus 1, we have s, we have, we break that into 2, because this right here is what we call the internalized studentized residual, and we covered that in either in one of the earlier videos. I want to say 64, 65, I don't really remember. Oh, 65. And so we have k plus 1, but all of these values can be calculated from one regression for no matter what I we use, and so that's kind of neat there. So now the last influential measure in R that we're going to cover is a covariance ratio. And now it's the ratio of generalized variances. Now a generalized variance is the determinant of the covariance matrix. And it can be shown that the larger the number is, the more dispersed the data. So if we look at the variance of our least squares estimate beta hat, it is this. But then, of course, we have to estimate the model variance with the sample variance, and it's this. Now, the determinant of this is the generalized variance for this least squares vector. Now, we hope that the generalized variance, that this is a very stable estimate. That's the goal. But what the covariance ratio does, it fits the regression line, comes up with estimates, removes observation I, fits the regression line, comes up with least squares estimates, and if these and then calculates the generalized ratio for each of those, right? So now if the generalized variance is very similar to these, it says that the dispersion around our least squares estimate is very similar, and that says that ith case is not influential. But if these two values differ by some, a significant amount, then that says case I is influential. It changed the dispersion of our least squares estimates. And the rule of thumb is if the covariance is greater than this value, or if it's less than this value, then we classify case I as influential. And as the other ratios, that to me it seems like that you have to fit two models, and then for each I you have to fit n models, or n plus 1 if you count the full model. But that's not the case. Every one of these can be calculated from just one regression fit, and this is how you show it. So all n covariance ratios can be calculated from one regression. Now from previous video 48, we showed this relationship. And so what we do is we stick this in for this here. But every one of these is fit from the full model. So for each I, so when we remove I, we just go down one row in the design matrix and one diagonal element in the hat matrix, and we can recalculate this very, very, very quickly. And so with that substitution, the result follows, and we'll leave it at that. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.